And layout are the 3 topics. So here's an outline of the talk. And so let's first talk about sketching. So what do I mean by sketching? I mean the obvious. You're interested in phylogeny and you want to set up a phylogenetic tree or network and you just want to draw it. And you want to draw it in such a way that the Newick, so that, that it's captured as a graph. It's not just a bunch of pixels, but you can then do different things with it. You can change the layout, use it for input to some algorithm that you're developing, and so on. So that's part 1 of the talk done. Part 2, it's going to be a quick talk. I've only got 8 minutes. So capture, what do I mean by capture? Well, if you've ever tried to get Newick strings for images of trees or networks that you've seen in the literature that you like, you'll see that biologists never give you that. They give you the raw data. Here's the raw data, good luck reproducing what we've done here. So the obvious idea is you want software that allows you to take an image, put the image into the software, and then capture the network or the tree as a data structure. Okay? And so that's what capture is about. And so here's a video how you do that. You put the picture in, tell the program where the root is, and then it doesn't do a perfect job. So you have to go in there and then edit. You have to fix up stuff that will miss and so on. And so this is a algorithm, traditional algorithm where you follow pixels around. You might be asking yourself, well, why don't you just use ChatGPT? And you can use ChatGPT. You can give ChatGPT an image of a tree, and it will find the taxa for you, and it will give you a Newick string. But that Newick string will not reflect the topology of the tree. It will be some other tree. And if you give it a network, it gives you a Newick string that's just broken. So at the moment, at least, and AI is not the answer. Yeah, so you need something, and this is like a combined, the algorithm does some of the work, but you have to go in there as a user and then clean up stuff. But that works well. So I've done that with lots of networks and trees that I've been interested in. I've been able to capture them. So that's part 2 of the talk. Now part 3 is going to be slightly longer, so this can be more algorithmic, how to lay out a network. And so if there's one take-home message from this talk, is that if you've got a phylogenetic network, a rooted network, there are 2 different ways to draw them. One we could call the transfer view. So in this picture here that represents speciation by hybridization in fish, the visualization that the authors did was something like that, like you see there. The transfer view is where you draw a tree, basically, and then you have a couple of edges going between different parts of the tree, transferring stuff. Okay, and that's one way to draw a phylogenetic network. The other way, let's call it the combined view. So I'm proposing these terms. Nobody uses these terms yet. Maybe they might catch on, they might not catch on. But in the combining view, when you have a reticulation node with incoming edges, those are drawn in a similar way. So you don't have one favored edge, which is the tree edge coming in. You have everything's combining. And so the combining view is something that you'd use when you're trying to represent speciation by hybridization, say, where 2 genomes are thrown together and the amount of genetic material passed down is roughly equal, whereas a transfer view is that situation, horizontal gene transfer, where you've got mainly one genome coming down one of the edges, and you've got a couple of genes coming through the other edge. Okay, so it does, in both cases, it's the same graph. As graphs, they're exactly the same, but you're visualizing them in different ways. And it does make a difference how you draw your network. Okay, how to lay out a combined network. So how do you draw a network? So here's a picture of a network, and how did I get to this picture? Well, the basic idea that everybody seems to use is that you identify a tree and compute coordinates for the tree and then use those coordinates for your network. And so in this case, we call it, let's call that the backbone tree. And for a combined view, what you do is for each reticulation node, you find its last stable ancestor. That's the last node on the path from the root. The last node on the path from the root down to the reticulation node, that's on all paths. Okay, so it's the last one before things start branching out. And then so now the tree that we're using for the layout is everything in blue and not those oranges, reticulation edges. So if I've got one ordering or embedding of the tree, that gives rise to one particular drawing of the network. And in this case, it looks nice. So what we see on the left is pretty much what we want. But take that same tree and embed it slightly differently. Instead of A, B, C, D underneath P, I've changed the order to A, D, C, B. I get perfectly good embedding of the tree, but now if you look at what it means to the network, that doesn't look so good. So we like the one on the left, we don't like the one on the right. So how do we distinguish between, how do we make sure that when we're using a tree to draw our network that we use the right embedding of the tree? So I've come up with a score, the OD score. It's not what you think, it's orthogonal displacement. Okay, and so the basic idea is you look at how much up and down is going on with the reticulation edges. So on the left, it's 2 plus 1 plus 2, 1 plus 1, that's 5. Over here, it's 2 plus 1 plus 3 plus 1 is 7. So the network on the tree embedding on the left has a better score, and it leads to a nicer drawing of the network. And so you can set that up as a computational problem. You can show that the decision problem is MB complete, and so luckily it's all hard, so that means I can come up with a heuristic. So the heuristic here is you do a post-order traversal of that backbone tree, and then for each node you rearrange the children in an attempt to minimize the OD score. And if you don't have too many children, up to 8, say, you can look at all possible permutations. There's not too many of those, and otherwise you have to use, in this, I'm using simulated annealing. Okay, what about a transfer network? What's the backbone for a transfer view? For transfer view, for each reticulation node, you have to say which of the edges is the transfer acceptor edges, which is the one that's going to be drawn like a tree edge. So if you have a combining view, you've got to go in there, and you could do that, say, in the Phylogenies program where you select an incoming edge for each of the reticulations, press the appropriate button, and then ask it to redraw. And you can see that it's the same network, but you can see it's drawn quite differently. It has a different interpretation. We've chosen one transfer acceptor edge for each reticulation. Here's a network from that I found recently from a paper at 2023, and it looks fantastically complicated. You've got these transfers going up and down and going up and then coming back down and so on. So I think that's just an artifact of the fact that the authors were not using an algorithm that knows how to draw a transfer network. So if you take that, capture that network and put it into the program, you get a much nicer, cleaner looking. It's less exciting because there's not all that stuff going up and down and crossing over, but it's probably a better visualization. So there is related work. Computer scientists are looking at binary trees with undirected edges between the tree edges, and they explicitly go for the crossing number, minimizing that. I couldn't figure out how to do that in a more general case, so that's why I was using the OD score. Yeah, and so here's an example from their paper with a minimized crossing number, and that's what my algorithm does. It's pretty similar. You don't lose anything, I don't think, by going for the OD score rather than directly for the crossing number. Yeah, and that's all I had to say. Thank you.
Okay, that's going to be a hard act to follow. So I think we'll have another quick changeover, or maybe a question whilst the changeover is happening. Does anybody have one? Really? So do you think that it will change the perception of horizontal gene transfer and more complicated evolutionary stories as a thing that people need to communicate?
I think people, first of all, have to distinguish between transfer view and combining view. Quite often they get that just wrong. They're you're depicting horizontal hybridization, but you're drawing it in the transfer way. We saw that example there, and sometimes people do the opposite. And I think a better picture, a cleaner picture is always going to be more useful. Yeah, thanks.
Thanks very much.